We want to look at several stoichiometry in solution problems. Again, there are some drills within the module for you to practice these, but I want to also talk you through a typical solution to one of these problems. You know, the essence of solution chemistry is, of course, that we talk about a solution's concentration in terms of its molarity, moles per liter. And as I'm going to be emphasizing, whenever we use molarity as a conversion ratio, you want to explicitly write out the full expression of what we mean by molarity. So, for example, I'm going to start by using the example of the balanced chemical reaction between a solution of silver nitrate, and I indicate that by writing aqueous behind it, and sodium phosphate solution, again aqueous, to form a precipitate of silver phosphate, and I would always tell you what the precipitate was in one of these double displacement reactions, and then plus sodium nitrate, which is soluble in water. In fact, all sodium compounds, in fact, all group 1A compounds, and also all nitrate compounds are soluble in water, which tells us definitely sodium nitrate would be soluble in water. Let's imagine I had a 0.15 molar solution of silver nitrate and a 0.25 molar solution of sodium phosphate. Furthermore, let's imagine I took 11 milliliters of the silver nitrate solution and then ask the question, how many milliliters of the sodium phosphate solution should I be using to completely react out all the silver nitrate solution? You know, in previous stoichiometry, we've seen I might give this in terms of mass. So many grams of silver nitrate, then how many grams of sodium phosphate do I need? But the truth here is that in solution, nobody asks about how many grams of a solute we have. Instead, we want to know volumes of solution. So question A here is how many milliliters of the sodium phosphate solution react with, let's just say, 11 milliliters of the silver nitrate solution. Now, one of the important points here, of course, is to always pay attention to the stoichiometry. Notice it's 3 moles of silver nitrate for 1 mole of sodium phosphate. So if I start out here with a given 11 milliliters of the silver nitrate solution, and I just gave as an example here that my concentration is 0.15 mole of silver nitrate for every 1,000 mils of solution. And notice here how I write out 0.15 moles per 1,000 mils. Then I write 1 mole of sodium phosphate for every 3 moles of silver nitrate. There is always a stoichiometry relationship in any of these kinds of calculations. And finally here, the last step is 1,000 milliliters of the solution of sodium phosphate contains 0.25 moles of sodium phosphate. And when you do the arithmetic, it works out you need 2.2 mils of the sodium phosphate solution. Notice the pattern is always going to be the same in these kinds of problems. I start with a volume of one solution, convert it to the numbers of moles by applying the molarity as moles per 1,000 mils, use a stoichiometry ratio between the two substances we're talking about, and then finally I use the molarity of the second solution upside down. That's the whole point about ratios. They can always be written one side or the other to convert the moles of the second reagent, in this case of sodium phosphate, into the equivalent volume given a particular concentration. Notice the only time mass comes into any kinds of questions involving solution chemistry is if somebody asks something about a solid material that appears. For example, from part A here, how many grams of silver phosphate are formed in this reaction? Notice I could start with either the 11 mils of the silver nitrate solution or the 2.2 mils of the sodium phosphate solution. The point is those are the stoichiometrically balanced quantities of those two solutions. I'll just start with a given. I was given 11 mils to begin with here of the silver nitrate solution. And again, of course, that solution is 0.15 moles of silver nitrate for every 1,000 milliliters of solution. And then again, notice the stoichiometry is also 1 mole of silver phosphate. Now we're looking at the quantity of silver phosphate for 3 moles of the silver nitrate. And then finally, since we're now asking about a weight, it's 420 grams of the silver phosphate make up 1 mole of silver phosphate. And notice it's very important to remember that the 0.15 moles silver nitrate per 1,000 mils of solution, because when you include that 1,000 in the arithmetic here, this comes out to 0.23 grams of silver phosphate. Notice I'm getting a 2 sig fig answer based, by the way, on the fact the volume and in fact the molarity also here of the silver nitrate were both given as 2 sig fig numbers. I took basically 3 sig figs on my weight for the silver phosphate, but that's perfectly, doesn't matter whether or not you do that or not. But in any case, the important point here, again, we're starting with a volume of the solution, applying the molarity to figure out the moles. You always use molarity with a solution, then a stoichiometry ratio, and then finally, since now we are asking about a weight, of course I apply the molar mass to solve that problem. And the third question I'm going to give you here is a different kind of problem. I'm going to use a different chemical reaction. We're going to look at the reaction between solution of lead 2 nitrate. Remember, you need 2 there because lead has a +2 charge, and it's one of those metals in the transition block that has several different possible charges, plus a solution of hydrochloric acid to form lead 2 chloride precipitate, and then you would also make 2 nitric acids, which would remain soluble in water. And the question here is, if I ran a reaction in which I took 10 milliliters of an HCl solution of an unknown molarity plus excess lead 2 nitrate solution, and let's just say for the sake of argument I got 0.175 grams of the lead 2 chloride precipitate. The question is then, what's the molarity of the HCl solution? This is an example of what is basically a titration type reaction, in which I'm starting with a fixed volume of an unknown solution, reacting it with excess of the other solution, and weighing the precipitate. These to find out what the molarity of this unknown solution was. The point of this is these are always 2-step problems. In other words, if I've told you that I made 0.175 grams of lead 2 chloride, you certainly know how many moles that is, because 1 mole of lead 2 chloride, according to the periodic chart, adds up to be 278 grams of lead 2 chloride. You can, of course, look up the weight of lead and the weight of 2 chlorides, and that adds up as a 3 sig fig number to 278. And notice I gave you 3 sig figs in the weight, 0.175 grams of lead 2 chloride, so I should use a 3 sig fig weight. Then the other part of this is, of course, it takes 2 moles of HCl to react with 1 mole of the lead 2 chloride, or I should say to make 1 mole of the lead 2 chloride. So when I do this arithmetic, it comes out to 1.26 times 10 to the minus 3 moles of HCl are being formed in this reaction. The molarity, because that was the question, remember, the molarity is defined as how many moles of HCl do I have for 1 liter of solution. Well, what I know is that in my experiment I had 1.26 times 10 to the minus 3 moles of HCl in a total volume of 0.0100 liters of solution. Notice it's because remember we said we started with 10.0 mils of the HCl solution. And so the molarity here works out to be 0.126 molar HCl. Notice this is a very typical situation here, that when somebody asks you what's the molarity of the solution, the first thing you should do is write down, what do you mean by molarity? It's moles of the solute per liter of solution. And you know, usually you have one of these numbers given to you right away. That's usually, in these cases, the volume. I said I had 10.0 mils of solution, and so therefore that's the volume. Now I need to know the moles, and that's what I did the stoichiometry calculation for, to figure that out. We'll see other examples of this in acid-base chemistry. These kinds of titration-type calculations are important, and you want to remember here, it always ends up being a 2-step calculation. First to find the moles of the unknown, and then to find its molarity by taking the moles and dividing it by the volume of its solution.